So FSW 10 megahertz. So how do we choose L and C now? Your ripple spec. Okay. So delta V out, how much was that? Anybody remembers? VDD into D 1 minus D over 8 LC FSW square. Okay. VDD we know 1.8 volt and we know this will be maximum at 50% duty cycle. So, we will take the worst case 0.5 into 0.5 over 8 LC. So, let us say my ripple spec is, and this spec will be given, assume delta V out is less than 10 millivolt. So, 10 millivolt is the worst case. So, let us see. So, 10 millivolt is the max number. So, the worst case you have to, which means whatever the variations in L and C, considering that everything, it should not be more than 10 millivolt. So, when you design at a typical case, you have to have some margin. So, usually typical case you will target 5 millivolt also, okay, because your L and C will have some tolerances. So, and those tolerances may be plus minus 20% also. So, this LC product may see a huge variation. And then FSW also you have to, how much variation you have in the switching frequency, because you will be designing on chip oscillator. That oscillator may also vary across process voltage and temperature. So, even if it is a 10%, so that 10% you also have to consider. So, which means LC equal to how much? 10 millivolt, sorry, 1.8. How much will be this? 0.25 divided by 8 into FSW we know 10 megahertz 10 power 6 square into 10 millivolt. How much is this? So, this becomes 0.45 pico? Oh, how come pico? Huh? Pico what? Over 8 into 100 into 10 power 12 into 10 power minus 2. Okay. So, you get 0.45 over 8. So, this goes away. 0.45 divided by 8. So, you get 5.6 into 10 power minus 14. Huh? What will be the unit? Second per? No, 1 over square root LC is radian per second. So, second, yeah, second by radian per. Okay. So, how do we choose L? So, one you have to fix, you have to calculate the other. Huh?
We have the ability to pick undershoot overshoot.
No, undershoot overshoot is fine. Okay. I mean, what do you guys think 10 megahertz the L should be? What kind of number? So, I mean, theoretically, you cannot directly say that, okay, you have to choose L this and that. One thing I told you guys that choosing the L smaller and higher L for the same LC product will give you a better transient response, but then it will increase your inductor ripple current. So, you have to go back and calculate your RMS losses. I mean, so far we have been considering that your ripple is small. So, I square R loss, we are not taking the RMS effect, we are only taking the DC. So, if that ripple becomes larger, so let us say I mean uh, 1 amp is the load current and your peak to peak ripple is like 1.5 to 2 amp. So, your peak will be like 2 amp kind of thing. So, your RMS losses will be much higher in that case. So, it will start dominating. So, if you are choosing a very small L, then you have to make sure that you go back and calculate your RMS losses and make sure that your efficiency is not hampered that much. Okay. So, let us say if I assume L equal to, so there is a one, I mean this comes from uh, the experience actually, people have been designing, and if you look at the trend actually, the inductor size, take any products and you will find actually, so for lithium ion battery, L is 1 micro Henry for, sorry, not 1 megahertz, for 3.3 micro Henry 1 megahertz, which means if you go at 3 megahertz, it will become roughly 1 micro Henry. When you go to 6 megahertz, it will become 0.47, 0.5 micro Henry, and that is how it scales actually. You pick any product, you will see the similar numbers. Okay. And the reason is this is the optimum value for the range of voltages you are looking for, because lithium ion battery, I already told you the max voltage will be 4.6 volt or so. 4.6 volt the typical, but usually they are designed for up to 5.5 volt. Okay. So, considering all those factors, 3.3 will give you the optimum, 3.3 microhenry will give you the optimum value for which you get a decent efficiency, like you can achieve up to 90% also, which means your RMS losses will not be that much and you can still achieve decent transient response. Okay. But now we are looking at 1.8, this is for 5 volt, 1.8 volt means 2.5, like we can look at a 1, roughly 1 mega, 1 microhenry kind of thing at 1.8 volt. Okay. Okay, let us take factor of 2. The factor of 2 I am considering because lithium ion battery spends most of the time at 3.6 volt, and that is where you actually optimize your efficiency. So, for VDD, lithium ion battery means VDD, I will say typical equal to 3.6 volt. Okay. L equal to 1.15, sorry, 1 point, how much will be that? 1.65 microhenry for 1 megahertz. Ten megahertz, you can easily choose how much? 165 nanohenry. Nanohenry. C, how much will be the C? So 5.6 into 10 power minus 14 divided by 165 into 10 power minus 9. So this becomes 560 over 165 into 10 power minus 7. 3.3 microhenry for 1 megahertz. Higher frequency means lower L. Okay. When I say 3.3 microhenry per megahertz, that does not mean that if you are increasing the frequency, then you have to multiply simply. If you are getting confused with this, then let me write this for. Okay. So how much was the cap value? What is the cap value? 0.34 340. So do you guys think this will be enough, this cap, to meet the transient? Okay, so you can meet the ripple spec, but for the transient you have to calculate. And so one way to calculate is, let us say the worst, what will be the worst case? Your inductor doesn't supply any current during transient and all of the current is supplied by your capacitor for the duration of how much? During the rise time of the inductor. Okay. So, and rise time of the inductor you can, so let us say 1 amp current and you know the inductor value, so which means you know the slope, correct. So, let us say for 50% duty cycle you are looking at 1.8 volt input and 0.9 output. So, what will be the slope? V in minus V out over L, 0.9 over L. How much is that? 500 milliamp kind of thing? How much?
Actually, V in minus V naught by
L, how much is that? So, you have to multiply that by, your time. So, let us say you stretch your duty cycle to 100%. So, 100 nano. So, how much it will rise in 100 nanosecond?
into the time you have to multiply.
Yeah.
5.45 milliamp.
Okay, but the one thing you have to calculate actually, but if you want to calculate the exact number, then you have to basically look at the triangular waveform, how much charge is supplied by the inductor and how much capacitor is supplying. Okay, because your inductor current will be rising, but at not at the same rate at which load will change instantaneously, but this will have a some slope, okay, finite slope. So, that difference will be supplied by your capacitor. So, from there you can calculate, and based on that you will know how much. Or another way, if you want to limit it by your bandwidth, then you can just make your bandwidth 1 over bandwidth as a delay, and from there you can calculate. Okay, so let us say this is order of how much, 1 megahertz bandwidth for 10 megahertz frequency. Okay, so 1 microsecond delay. Okay, so but you have to add 2 pi factor there actually, because that is in radian per second if you are looking at FSW. Okay, so from there you can calculate. So, one is the bandwidth limited, but if you are not limited by bandwidth, then you will be limited by inductor slope, current slope. Okay, inductor current slope means you have instantaneous change in the duty cycle. I mean, you can in the next cycle, whenever your load change happens, you stretch your duty cycle to 100% right away. But that is not true if you are limited by bandwidth, because it will not change your control voltage from, let us say you have a 0.5 volt control voltage for 1 volt ramp, when you are operating at around 50% duty cycle. So, from 0.5 it will not right away go to 1 volt in the next cycle, it will take some time because of that compensator. Okay. But if you are have some other control technique, non-linear, we will talk about that, there it is possible, it can the next cycle it can provide you 100% duty cycle, then you will not be limited by bandwidth, but you will be limited by the inductor slope, current slope. Okay. So, your transient will be better in that case, but here you are limited by bandwidth, so then your capacitor requirement might be larger here. Okay. So, I will tell you formula, you can for a particular delta out, how you calculate the C when you have a limited bandwidth. But for sure this is not enough actually, usually the cap requirement is 10 times of your inductor value, and usually that is how you keep. If you have a 1 micro Henry inductor, then you try to keep your capacitor value 10 microfarad also. Then you have to consider plus minus 10% tolerances. So, let us say your inductor has increased by 20%, capacitor has decreased by 20%. It is quite possible, your tolerances are random, one may increase, other may decrease. So, that will be the worst case. So, then you have to consider that and you have to keep some margin. So, whatever your theoretical calculation, usually keep 2 times of the cap. Okay. So, if your theoretical calculation say 1 microfarad, then you just choose 2 microfarad, so that you will still get 1 microfarad considering all those tolerances and other variations. Okay.